In this example, we're analyzing a position versus time graph, and we want to learn things about the object's motion through this analysis. The first thing we want to know is, when is the object moving fastest? Well, remember, the slope of a position versus time graph is an object's velocity. So if we want to know where the object is moving the fastest, we want to find the place in the graph where the slope is the steepest. So we need to look at different parts of this graph and try and find the steepest slope. Well, let's start at the very beginning. From 0 to 1 second, the graph rises. It goes from a position of 0 to a position of about 3 meters in 1 second. So that's a slope of 3 over 1. Is that the steepest part of the graph? Well, the only way we're going to find that out is to compare it to other parts of the graph. Look at what happens from 1 second to 3 seconds. During that time period, the graph is still rising, but not as steeply. From 1 to 3 seconds, the position goes from about 3 to about 5 maybe. That's only 2 meters over 2 seconds. So the slope is much more gentle in this region. In the next region of the graph, the slope is even more gentle. In fact, it's very close to 0 because the graph is pretty much flat during that region. Now let's look from a time of 4 seconds to 9 seconds. During that time, the graph is falling. Now, falling just means a negative velocity, and negative just means direction. So we don't care whether the graph is rising or falling, we just want to know where it's the steepest. So this could be the fastest velocity. However, if you look at it, from 4 to 9 seconds, we go from a position of about 5 down to a position of about 0. So it took 5 seconds to drop about 5 meters. That's a slope of about -1. So still, our slope of 3 is the steepest slope we found so far. Well, let's continue comparing then. From 9 to 9.5 seconds, the graph is flat. That means velocity is 0. So the object isn't even moving during that time. But look what happens from 10 to 11 seconds. From 10 to 11 seconds, the position changes from -1 meters to -10 meters. That's a very steep slope. In just 1 second, the position changed by 9 meters, so that's a slope of -9. Now, we don't worry that it's negative because remember what negative means. That just means direction. The object is moving in the negative direction at that point, but it's moving the fastest that we've seen so far. Does the object move faster anywhere else? Well, the next section of the graph is flat, so that means the object isn't moving during that time at all because the slope is 0. And in the final section of the graph, from 12 seconds to 13 seconds, the graph rises. It rises from -12 to about -8. So that's a change in 4 units in 1 second. So that's steeper than our original slope. But the very steepest slope we found was from 10 to 11 seconds. So that's where the object is moving the fastest. The next question asks, how many times does the object change directions? That's where we have to worry about the sign of the slope, because sign indicates direction. If the slope is positive, the object is moving in the positive direction. If it is negative, the object is moving in the negative direction. So if we look at the graph, we'll see that from 0 seconds to just over 3 seconds, the slope of the graph is positive. It's rising the entire time. So during this time, the velocity is positive, or the object is moving in the positive direction. The graph then stays flat for a few moments, indicating the object is not moving at all, and then, from just under 4 seconds to about 9 seconds, the slope is negative. This means the velocity is negative at this point, which means the object is moving in the negative direction. So that's a direction change. The object started out moving in the positive direction because the slope was positive, but now that the slope is negative, the object is moving in the negative direction. Now in the next section of the graph, the object's position becomes negative, but the slope is still negative. So the slope is still negative, that means the object is moving in a negative direction. From 9 seconds to about 9.5 seconds, the object did stop because the slope is 0, which means the velocity is 0, but the object never changed direction. Prior to 9 seconds, it was moving in the negative direction. After 9.5 seconds, it was moving in the negative direction. And between 9 and 9.5 seconds or so, it was simply stopped. However, if we go on to the next section of the graph, from 12 to 13 seconds, there we see the slope is positive again. The graph is rising. That means the velocity is positive, which means the object is moving in the positive direction, so that's a direction change. So how many direction changes did we have? We had 2. The object changed direction twice. The next question asks, what's the instantaneous velocity of the object at 11.8 seconds? Well, the instantaneous velocity is simply the slope of the graph at that time. If we look at 11.8 seconds, the graph is flat. It's not changing at all. So the slope is 0, and that means the instantaneous velocity is 0 at that time. The final question asks, what is the instantaneous velocity of the object at 6.0 seconds? Well, if we look at 6.0 seconds, the graph is definitely not flat, so we're going to have to calculate a slope. If we look from about 5 seconds to about 9 seconds, the slope seems to be pretty constant. That portion of the graph looks like a straight line. So, if I calculate the slope of that line, that's the slope at any point during that time interval, so that's the velocity at any time during that interval. So what's the slope during that time? Well, the slope, which is the velocity, is simply the rise over the run. In other words, the change in the y-coordinate divided by the change in the x-coordinate. Well, during this time, the object starts at a position of 4.0 meters and ends at a position of 0.0 meters. So if I take the final position, 0.0 meters, and subtract the initial position, 4.0 meters, that's the change in the y-coordinate. The change in the x-coordinate, which is the time, is simply the final time, 9.0 seconds, minus the initial time, 5.0 seconds. So now I have the change in the y-coordinate over the change in the x-coordinate. That's the rise over the run, and that's the slope. If I work these numbers out, I get negative 1.0 meters per second. So the velocity of this object over this entire time interval is negative 1.0 meters per second. So that's also the velocity of the object at 6.0 seconds. Let's end by discussing significant figures a little bit. When you were taught how to make measurements, you should have been taught that when you read a scale, you can always approximate your answer to the next decimal place in the scale. So, if the scale is marked off in units of 1, you should report your answer to the tenths place, the next decimal place. Well, if we look at this graph, the time is marked off in individual seconds. So we should read the time from the graph to the tenths of a second, and that's why my times are 9.0 seconds and 5.0 seconds. In the same way, the position is marked off in units of 2 meters. The next decimal place would be the tenths place, so that's why my positions are 0.0 meters and 4.0 meters. Well, then when I subtract, I have to use the rule of subtraction, which says report your answer to the same decimal place as the least precise number in the problem. So when I take 0.0 minus 4.0, I get negative 4.0. And when I take 9.0 minus 5.0, I get positive 4.0. At that point, I divide the two, and there I count significant figures. And since both of those numbers have two significant figures, the answer has two significant figures. And that's why the final answer is negative 1.0 meters per second.